Right now, a spacecraft built in the 1970s is traveling through a region no human being has ever visited. It is farther from Earth than any other working machine in history. It was designed before the personal computer, before the modern internet, and before many of the scientists now studying its signals were born. Its original mission was expected to last only a few years. Instead, nearly half a century later, Voyager 1 is still communicating with Earth. Its signal is weak, its power is fading, its hardware is ancient. Yet the information it continues to send has forced researchers to rethink what exists beyond the protective influence of the sun. This is not only a story about an old spacecraft surviving longer than anyone expected, it is also a story about the boundary that protects our solar system, the strange environment beyond it, the engineering effort that brought Voyager back from near silence, and a historic distance milestone approaching in 2026. By the end of this story, the night sky may feel very different. Voyager 1 began its journey on September 5, 1977, when it launched from Kennedy Space Center in Florida. The plan sounded straightforward. The spacecraft would fly past Jupiter, continue towards Saturn, photograph both worlds, collect scientific measurements, and then move outward until its mission ended. NASA expected a successful lifetime of roughly 4 or 5 years. Voyager 1 quickly exceeded that expectation. In March 1979, it passed Jupiter and returned close-up views that transformed humanity's understanding of the giant planet and its moons. In November 1980, it reached Saturn, captured another remarkable collection of images, and continued outward. The spacecraft gained speed by using the gravity of the planets as a slingshot. Each encounter changed its path and sent it deeper into the outer solar system. By the end of the 1980s, Voyager 1 had traveled farther from Earth than any human-made object before it, yet it remained active. It continued measuring particles, magnetic fields, and radiation, while sending an increasingly faint radio signal across billions of miles. Engineers today look at its technology with amazement. Its onboard computers are primitive compared with modern devices. Its memory is tiny. Its systems were never designed for decades of operation. Still, careful engineering, redundancy, and constant mission support allowed the spacecraft to survive. Then, in 2012, Voyager 1 crossed a boundary that changed the meaning of the mission. That boundary is called the heliopause. To understand it, imagine the sun not only as a source of light and heat, but also as a source of a continuous stream of charged particles. This stream is called the solar wind. It flows outward in every direction and creates an enormous bubble around the sun and the planets. That bubble is the heliosphere. Inside it are Earth, the other planets, countless smaller objects, and every spacecraft launched before Voyager reached the edge. The heliosphere acts as a protective region shaped by the sun's magnetic field and solar wind. Far beyond the planets, the solar wind weakens. Eventually, pressure from the interstellar medium pushes back. The dividing region between the sun's influence and the space between stars is the heliopause. When Voyager 1 crossed that boundary in 2012, it became the first human-made object to enter interstellar space. That achievement was not symbolic. For the first time, humanity had an operating scientific instrument outside the heliosphere directly sampling the environment between star systems. Until then, interstellar space had been studied from a distance. Scientists used telescopes, mathematical models, and indirect measurements to estimate its density, temperature, magnetic structure, and behavior. Many models described it as thin, cold, and comparatively quiet. Voyager 1 found something much more complicated. Beginning in 2017, its plasma wave instrument detected a persistent, narrow-band signal within the interstellar plasma. Instead of a single burst or an isolated event, the spacecraft measured a faint, continuing hum over an enormous distance. The signal remained detectable as Voyager traveled through more than 900 million miles of interstellar space. For comparison, Earth is about 93 million miles from the Sun. Voyager detected this phenomenon across a region roughly 10 times that distance. Researchers concluded that interstellar space is not simply a smooth, empty background. It contains structure, motion, density changes, and turbulence across many scales. The space between stars has texture. It may look empty to human eyes, but it is filled with charged particles, magnetic fields, waves, and changing conditions. Voyager's measurements provided the first continuous view from inside that environment. That discovery matters for more than abstract physics. The heliosphere helps protect Earth and the inner solar system from high-energy cosmic particles. Many of those particles originate in violent events such as exploding stars. The sun's magnetic influence deflects and reduces part of that radiation before it reaches our region. If the interstellar environment pressing against the heliosphere is more variable and energetic than expected, scientists must reconsider how stable and predictable that protective boundary really is. Voyager 1 has not shown that Earth is in immediate danger, but it has shown that the system surrounding and shielding us is more dynamic than earlier models suggested. The border of our solar system is not a quiet wall. It is an active interaction zone. The story became even more dramatic in late 2023 when Voyager 1 appeared to suffer a potentially fatal malfunction. The spacecraft continued sending a radio signal, but the data inside that signal was unreadable. Instead of organized scientific and engineering information, controllers received repeated patterns and corrupted code. Voyager was still responding, but it could no longer communicate clearly. For about 5 months, engineers at NASA's Jet Propulsion Laboratory worked to understand the problem. They eventually traced it to part of the flight data system. A memory chip had failed after decades of exposure to radiation and extreme conditions. That damaged section contained software needed to package scientific and engineering information before transmission. On Earth, a failed memory component can be replaced. Voyager 1 was roughly 15 billion miles away. No repair crew could reach it, no replacement part could be installed. The only available connection was radio communication, and every command required about 22 hours to travel one way. That meant a single round of communication took nearly 44 hours. Engineers would study the latest response, develop a theory, write instructions, transmit them, wait for the command to arrive, and then wait again for the result to return. Every step had to be deliberate. A mistaken command could have created a new failure or ended the mission permanently. The team developed an extraordinary solution. The damaged memory could not be repaired, so the affected software had to be moved. Engineers divided the code into smaller sections and placed those sections in other available areas of the spacecraft's memory. They also rewrote references, so the separated pieces could still work together as one functioning system. It was the equivalent of remotely reorganizing part of a computer's brain across billions of miles, using technology designed in the 1970s, with almost 2 days required for each exchange. In 2024, the effort succeeded. Voyager 1 resumed sending readable engineering information and then returned to transmitting scientific data. A spacecraft that many believed had reached the end of its life had recovered once again. And when it came back, it continued reporting the same strange interstellar plasma behavior that had already challenged earlier expectations. But some of Voyager's most important measurements came from the heliopause itself. Before the crossing, scientists expected a gradual transition. The solar wind would weaken, interstellar particles would become more common, and one environment would slowly blend into the other. Voyager 1 recorded something more abrupt and energetic. Near the boundary, charged particles were moving at extremely high speeds. Some measurements suggested temperatures approaching tens of thousands of degrees Celsius within the thin plasma. This did not mean Voyager passed through ordinary flames. The region is far too sparse for fire in the everyday sense, but individual particles carried enormous energy, creating what some descriptions called a wall of fire. The magnetic environment was also surprising. Researchers had expected the sun's magnetic field inside the heliosphere and the galaxy's magnetic field outside it to appear clearly separate. Instead, Voyager found evidence that the fields were connected and interacting. A process called magnetic reconnection can occur when magnetic field lines from different regions meet, break, and reconnect. This process releases energy and can create complex flows of particles. Voyager's observations suggested that the heliosphere and the surrounding interstellar medium are not isolated systems. Energy and magnetic structure can pass between them. That means the edge of our solar system is less like a sealed border and more like a changing, electrically active interface. The sun and the galaxy are linked at the boundary. This finding has major implications for models of cosmic ray protection, magnetic shielding, and the long-term behavior of the heliosphere. Voyager 1 forced scientists to replace a simple picture with a much more complicated one. Now the mission is entering its final phase. Voyager's power comes from 3 radioisotope thermoelectric generators. These devices use heat produced by the decay of plutonium-238 and convert part of that heat into electricity. At launch, the generators produced about 470 watts. Today, their output is far lower, near 250 watts, and it continues to decline by roughly 4 watts each year. The spacecraft is not failing because of one dramatic event. It is slowly losing the ability to operate its remaining systems. To extend the mission, NASA has gradually shut down instruments and heaters. Voyager 1 originally carried 10 scientific instrument packages. Most are now inactive. Each shutdown saves power, but everyone also reduces what the spacecraft can measure. These decisions are difficult because Voyager is the only working probe in its location. Once an instrument is turned off, a category of direct interstellar data may disappear. In 2026, another long-running instrument was switched off to preserve energy for the remaining mission. It had operated for decades and was still functional, but the power budget had become too limited. The mission team continues searching for ways to gain more time. One experimental approach involves changing how electricity is managed across the spacecraft. Engineers hope unused margins and lower priority systems might provide enough energy to extend scientific operations. Any such procedure is risky. Voyager's electronics are nearly 50 years old. Components have been exposed to radiation, cold, and decades of operation. A change that seems small on Earth could produce unexpected behavior aboard the spacecraft. Because of that risk, engineers plan to test power management methods on Voyager 2 before using them on Voyager 1. Voyager 2 has slightly different conditions and remains another invaluable source of outer solar system data. A successful test could open the possibility of restoring or preserving additional capability on Voyager 1. The team is cautious, but history gives them a reason to keep trying. Voyager has survived problem after problem that once seemed final. There is also a milestone approaching that captures the scale of the mission better than almost any number. According to the timeline used in this story, on November 18, 2026, Voyager 1 will reach a distance of 1 light day from Earth. A light day is the distance light travels in 24 hours. At that point, even a radio command moving at the fastest possible speed in the universe would require an entire day to reach the spacecraft. A reply would need another day to return. A command sent Monday morning would not complete a full exchange until Wednesday morning. No human-made object has ever operated at that distance. Voyager will cross that threshold while still moving, still listening, and possibly still transmitting. Every hour, it travels roughly another 38,000 miles into interstellar space. The delay increases, the power declines, the signal weakens. Eventually, likely in the early 2030s, the spacecraft will no longer have enough electricity to operate its scientific instruments or transmit useful data. At some point, Earth will receive a final signal. Then there will be silence. But Voyager 1 will not stop moving. Interstellar space contains almost no resistance. There is no atmosphere to slow the spacecraft and no nearby object expected to capture it. It will continue along its path for thousands, millions, and perhaps billions of years. Attached to Voyager is an object designed to survive long after its electronics fail. The Voyager Golden Record is a gold-plated copper disc containing sounds, images, music, and greetings from Earth. It carries spoken messages in 55 languages. It includes natural sounds such as rain, ocean waves, and animals. It contains human laughter and music selected from cultures across the world. The record also includes scientific diagrams and instructions intended to explain where Earth is located and how the information can be played. Its creators described it as a message in a bottle placed into the cosmic ocean. The chances of anyone finding it may be extremely small, but the purpose was larger than probability. The record says that a species once lived on Earth, learned to build machines, studied the stars, and sent evidence of itself beyond the solar system. Long after Voyager loses power, the record will remain. It may survive changes that erase cities, monuments, archives, and nations. It could continue traveling even after Earth itself becomes unrecognizable. That makes Voyager more than a scientific instrument. It is also a time capsule carrying a compressed portrait of humanity. Yet the most urgent reason to care about Voyager is not the distant future. It is the data arriving now. The persistent plasma signal first detected in 2017 gives scientists a continuous measurement of interstellar plasma density. Before this, researchers often relied on occasional disturbances. A major eruption from the sun could send a shock wave outward. Years later, that disturbance might reach the heliopause and produce a measurable response in the interstellar medium. Those events provided useful snapshots, but they were widely separated. Voyager's faint plasma hum offers something closer to a continuous record. As the spacecraft moves, it samples changes in density and structure. The result is a moving profile of the space between stars. That profile shows that interstellar space has something resembling weather. There are waves, disturbances, boundaries, and changing magnetic conditions. Structures can extend across enormous distances. The environment is not motionless, it is active and organized. Scientists are still debating the exact physical source of the persistent emission. One explanation is that it comes from naturally excited plasma oscillations. Charged particles vibrate and interact, producing a measurable signal. Another possibility is a phenomenon called quasi-thermal noise. That process would reveal density and temperature in a different way and could require researchers to revise parts of their models. Distinguishing between these explanations requires more data. Voyager 1 may provide some of it, but the spacecraft is running out of time. A future interstellar probe could answer the question more clearly, but no replacement is ready to launch. Even if a new mission began today, it could take decades to reach the heliopause. When Voyager 1 goes silent, humanity may lose its only continuous window into interstellar space for an entire generation. That is what makes the mission's final years so important. Every measurement is irreplaceable. Every hour of operation adds another point to a map no other spacecraft can currently draw. And every successful engineering decision delays the moment when that map stops growing. There is a larger lesson inside Voyager's story. The spacecraft is not the most powerful machine humanity has built. It is not the largest, the fastest, or the most advanced. Its computers are primitive, its memory is tiny, its remaining power is limited, its signal is difficult to detect. Yet it has done something no modern observatory near Earth can do. It went there. Some questions cannot be answered from a distance. A telescope can study light arriving from the stars. A satellite can observe the sun. A probe can explore a planet. But to understand interstellar space directly, an instrument must cross the heliopause and enter it. Voyager 1 had the patience, direction, and durability to make that journey. It survived far beyond its design life. It crossed a boundary no previous spacecraft had crossed. It found turbulence where models expected calm. It revealed magnetic connections where theories expected separation. It nearly lost its ability to communicate, then returned after engineers rewrote its memory from 15 billion miles away. Voyager 1 also reminds us that exploration is measured not only by speed or technology, but by endurance. The mission has continued because generations of engineers preserved knowledge, documented systems, and solved problems its original designers could never have anticipated. People who were not alive at launch now operate a spacecraft built by teams who have retired or passed away. In that sense, Voyager is a bridge across generations, as well as a bridge between the solar system and the stars. Its survival is the result of curiosity maintained over decades, one careful command at a time, across a distance that turns every conversation into a 2-day act of patience. And now it is moving toward one light day from Earth. Sooner or later, its power will fall below the level needed to continue. The final transmission will leave the spacecraft, cross the darkness, and arrive at Earth many hours later. After that, Voyager will become silent. But until then, the signal is still coming. It carries measurements from a region that humanity has only just begun to understand. It tells us the space between stars is more structured, more turbulent, and more connected than we once believed. One old spacecraft is still speaking from beyond the solar system. The question is whether we are listening closely enough. If stories like this are why you are here, subscribe and turn on notifications. Share this video with someone who would be fascinated by what Voyager 1 is still discovering, and leave a comment with the part of its journey that surprised you most.